Question 6, and we have a fairly tricky geometric series question in 3 parts. So all of these series have first term 1 and last term 1024, and initially the only common ratio we know is for series 1, and that's 2. Find n1, it says. So find the number of terms in the first sequence. Well, what do we know about the sequence? It's got a equals 1 and r equals 2, and we're told that the n1th term has value 1024. Well, recall the formula for the nth term of a geometric progression, and if we substitute what we know into that, we have that un1, or un if you want, is a times r to the n minus 1, or in this case 1 times 2 to the power n1 minus 1. Well, we're told that n1th term is 1024. I've just rubbed out the 1 times as well, so just solve that equation. 1024 equals 2 to the power n1 minus 1. That just gives you straight away n1 equals 11. You can use logs if you want, or you might just spot that, you might just know that 2 to the power 10 is 1024, and therefore n1 must be 11. It's a good thing to know, actually, 2 to the power 10 being 1024. I'd commit that to memory if I were you. Okay, part B. Well, I've written there r2 equals 4, because if you think about it, you're looking for, you need to start with 1, and you need to finish with 1024 by multiplying by an integer. Now we know it works for 2, because 1024 is a power of 2, it's the 10th power of 2. It's not going to work for 3, because if you write 1024 as its prime factors, it's literally just 2 to the power 10. Does it work for 4? Yes, it makes sense to work for power 4. Sorry, it's for base 4, doesn't it? Because if r is 2, we need to times it by 2 10 times. So if r is 4, we need to multiply by 4 5 times to get up to 1024. You can check that yourself. You just sort of have to spot this. There's not really a kind of proper way to solve that question, just to try different numbers until you find one that works, and you can logically reason that 4 is a sensible choice there. I don't think there's any others that will work. Well, to work out n2, just write the sequence out. It's probably the easiest thing. 1 times 4 is 4, times 4 is 16, just times 4 repeatedly until you get to 1024, and you can see very clearly there that we have 6 terms. Part C, now r3 is not an integer. Well, that's all very well. It feels like you can just pick anything, but remember, we have to finish at exactly 1024. So you're looking for a number that you can multiply by itself repeatedly until you can get to exactly 1024. Well, a sensible choice is to use a root of 1024. And what have we used so far? We've used the 10th root of 1024, which was 2. So we can't use the 10th root because that's an integer. We've also used the 5th root of 1024. That was 4. We've used both, that's series 1, series 2, basically written there. So for series 3, we need to use a different root of 1024. A nice easy option might be to use, sorry, I've just written down the number of terms there, of course, not forgetting that we would need 11 terms. That was our answer in part A. If we're using the 10th root, we need 11 terms, and if we're using the 5th root, we need 6 terms. So our sensible choice here might be the 3rd root, the cube root of 1024, which will need 4 terms in the sequence. Or you could do something different. In the mark scheme, it suggests using the 20th root of 1024, which is just the square root of 2. And that will need 21 terms in this sequence to get up to 1024. But I'm going to stick with this one, this cube root. And that gives us our value of r and our value of n. And if you use the formula for S4, then it gives you the answer 1137.